Alright, so what we're looking at right now is how to find real roots of polynomials. So we know that roots is just another word for zeros of a function or x-intercepts. So we've done this with quadratics, and we've done it a little bit with polynomials. So we're going to dig a little bit deeper into it. So finding zeros of a function, we can say that it would have at most n zeros for the nth degree polynomial. So if it's like a fifth degree polynomial, we can have at most 5 real zeros. So there's always 5 zeros, but some of them are going to be those complex zeros that we saw with quadratics. So the ones with the i's in them. So if it's an even polynomial, there's an even number of zeros, and an odd degree would give an odd number of zeros. So most of the time what we're going to do is factor, like we've been working on the past several days. So in the first one here, let's look at, we have 3 terms. So the first thing we're going to want to try, remember with all factoring, is to do greatest common factor. So there's a greatest common factor here of 3x to the third. So that gives us x squared left and plus 6x plus 9. So now factor what's left inside. So we have x plus 3 times x plus 3 would give us that quadratic. So the 3x cubed has to drop down. So this would be all factored out. Now we set each one equal to 0 and solve for x. So the first one would be 3x cubed equals 0, so x is 0 on that one. And then these two would produce both a negative 3. Okay? So there are, we're going to say, number of solutions, we're going to say there are 3. Okay? Well, technically there's 5 of them. We know, sorry, let's say there's 2 unique ones. Let's go there. We have a negative 3 and a 0. So there's 2 unique solutions. So go ahead and write unique there. Unique solutions. There's a total of 5 because of the power. We have 3 at 0, and we have 2 of them at negative 3. We're going to look at in a little while what that actually means for us. So the next one, I'm going to move the 36 over and factor it out. So add 36 to both sides, so we have a plus there. So I'm going to skip that step. But now we can factor out. So numbers that multiply to a positive 36, that would add to negative 3. So that would be 9 and 4. So both negative. Now both of these can go even further. So we have a x minus 3, x plus 3, x minus 2, x plus 2, so x values would be a positive 3, negative 3, or you can write plus minus 3, and then negative 2, positive 2. So we have 4 unique zeros. So go ahead and try the checkpoint there. So we would add 50 over. And then combine, we have 4 terms. So we do the first 2 terms. We do factor by grouping. X squared out. We're left with an x minus 2. Second 2 terms, so we have a negative 25x and a positive 50. So negative 25 comes out. And we're left with x minus 2. Put those together. X squared minus 25. We know we can break that down. And the x minus 2. So you can keep breaking that down to x plus 5 and x minus 5, or you can just set it equal to 0 right now and then solve for x, which we would have the square root of 25, which would be a positive and a negative 5. So either way works. So we have a positive 2 and a plus minus 5. So we have 3 solutions. So determine how many solutions each function will have, then use the given root or 0 solution of the polynomial to find all the other factors. So we've done this before too, so a little review. So we should have 3 answers here. So 3 solutions because of the power. Now we have the fact that negative 2 would plug into the function and give us 0 remainder. We could divide by that. So let's go ahead and do synthetic for negative 2. So 1, 6, 3, negative 10. Get a 1, negative 2, 4, negative 8, negative 5, and 10. So remainder is 0, just like we should get because it says 0. And now we can write that as a polynomial. So x squared plus 4x minus 5. And we can factor that. So factors to be positive 5, x plus 5, and x minus 1. So we know we have a solution. So x would equal negative 5. We have a positive 1. And this negative 2 is a solution as well. So we can go ahead and we can write that, just so we have our 3 solutions. Alright, so another one. So 7 works, so we have to divide out that. So 7, 1. We're missing x squared, so we put a 0. Negative 39. And negative 70. Get x squared plus 7x plus 10. Factor it out, numbers that multiply to 10, add to 7, 2 and 5. So I forgot I skipped the number of solutions. We should have 3 because it's a cubic. So we have x equals negative 2, negative 5, and that positive 7 that we started with. And so assume f of x is a polynomial of degree 3. So we're writing a polynomial here. So we know it's a cubic because it says degree 3. So that's key information there. They give us the fact that f of 2, f of negative 2, and f of 4 would be 0 if we evaluated it. So that means that these are zeros of the function, so x-intercepts. So write the simplest polynomial function. So if this would be x equals 2, x equals -2, and x equals 4, we can write these in factored form. Okay? So x minus 2 would be the factor, because if we set this equal to 0 and solve for x, we would end up with 2. We have x plus 2 and x minus 4. Alright, so that's equal to f of x. Now, if we wanted a function in factored form, we could leave it like this, but we're going to want to multiply this together. So we know that first set here would be x squared minus 4. We're going to multiply by x minus 4. So we get x cubed. We would end up with a -4x squared minus 4x and plus 16. If we were to multiply that all out, that would be our cubic function. So that's cubic in simplest form. That's what our answer would be. Okay? So it's going to take a little practice getting used to the writing polynomials. We kind of look at that. We already looked at that with quadratics, but this is just taking it a step further and writing it for any polynomial. All right. So the last part of these notes for the first part of section 5 would be multiplicity of a polynomial. So multiplicity of a polynomial just states how many zeros exist that are the same number. So we looked at an earlier example where we had 2 -3 values and 3 0 values. So x equaled 0 3 times and x equaled -3 twice. So that's multiplicity. How many of each 0 are there? So when a real root has multiplicity, the graph touches the x-axis but does not cross it. So it bounces off. So even means that it bounces. Okay, so look at the picture here. So right here at -3, it touches the x-axis but bounces back off in the other direction. That's what that means. So it's kind of reflected off. When a real root has odd multiplicity, so there's an odd number of them, it intersects. So right here, it touches the x-axis and it continues on through the x-axis to the other side. Okay, that would be odd multiplicity, that it passes through. So that's what we need to remember, is those two things. Even means bounce, odd means intersect. Okay. Example 4, we got for each graph below, determine the minimum degree of the polynomial, the number of zeros, and whether each zero has an even or odd multiplicity. Alright, so let's take a look here. Let's state our zeros first. That's the easiest thing. So we have a 0 at -3. We have one at 2. And we have another one at 5. Okay, so we are at -3, we're passing through. So it passes through. So multiplicity is even, or sorry, odd. So we're putting a 1 for multiplicity. We can say odd. I'm going to write both. So odd multiplicity. All right, and it's going straight through. We have a 1. So that means there's 1, x equals -3. We go over to 2, and this bounces off. It does not pass from negative values to positive values. It stays negative. So this is an even multiplicity. And it bounces. Well, we can say that's a 2. And we'll learn more about these in a little while. And then 5, so it's passing through, so that's an odd multiplicity. So 1. So minimum degree of the polynomial would be, we add these up. 1 plus 2 plus 1 is 4. That would be the minimum degree. All right, next one. So we have a 0 at -2. We have 1 at 0. We have another one at 1 and at 3. So we're bouncing at -2, which means even. I'm just going to write an E. So even would be 2. We have 1 at, bouncing at 0, so that's even. And we're going through at 1, so that's odd. And we're bouncing at 3, so that's even. Okay, so minimum degree, add those up, we would have a 7 for minimum. Alright, so we're going to do the same thing with not a graph, but zeros, like the actual function. So we know there are 2 -7s because of the square. So multiplicity of 2. The effect would be bounces. And then we would solve this one here. We would get a -1/2. There's only one of them, power of 1. So that intersects or passes. Whatever you want to write, pass or intersect. And then we have a +4 here. Multiplicity of 3. So that's an odd number, so that's going to pass as well. Next one we're going to have to actually factor out to get. So that would be x cubed minus 4x squared. We have to subtract this 16x plus 64. Alright, 4 terms, factor by grouping. We have x squared coming out. X minus 4. Oops, I need to write that. -16 out of the second group. X minus 4 inside. So put those together, we would have x squared minus 16 and x minus 4. So right here, if we factored this out, we'd have x plus 4, x minus 4. And this x minus 4 drops down. So we have a -4, multiplicity of 1, so that passes or intersects, so you could write that too. Either or works, pass or intersect. And then we have 2 4s, so we know that bounces. Go ahead and pause and try those checkpoints. Alright, this one we have to factor out. First thing we want to do, greatest common factor. So we have x out, oops, not equals, x out of there, so we have x squared minus 6x plus 9. Factor x minus 3 and x minus 3. So there's two of them. So we have an x at 0. There's one of them. We know that passes through. And we have a positive 3 twice. And that would bounce. Next one. Factor by grouping. Writing that parenthesis. Negative 4 out, so x minus 4 left, or sorry, 9, x minus 9. So x minus 9 matches, so we have a 0 at 9. If we pair these together, we would have a 2 and a negative 2 after we factored. So we have a negative 2, positive 2, and a positive 9. So all of them have multiplicity of 1. So these all pass through the x-intercept. Okay, so it's good to check at the end too, when we're looking at multiplicity of the function, that these should add up to whatever power that you have. Unless we have some of those complex zeros, but we're not going to look at those quite yet. So let me know if you have any questions. I will post another video on the next part of the notes.